Welcome to this lecture series in number theory. In this lecture, we'll develop a central tool in elementary number theory. So this is a very, very important lecture. And let us recall one relevant thing. So we have discussed previously the division with remainder theorem, which is a very basic fact, only enunciating that dividend is equal to divisor into quotient plus remainder. And the formal statement is that if you have any integer and you're dividing by, let's say, a natural number, then you can incur a remainder within this range. And divisibility, meaning the fact that D divides A, is equivalent to saying that this R is 0. And the Q and R are uniquely determined, of course, under this constraint. Very importantly, we need to know about relations for this lecture. In particular, we need to know about equivalence relations. And again, as I've said many times, that this is available as a few primers in my playlist named Kickstart. Or you can just do a quick Wikipedia or Google or wherever you can read about equivalence relations in 1,000 expositions. All right. Here are some problems for practice. And now let us get started. So we will define a relation on the set of all the integers with respect to a fixed natural number n. The fix in n, and now we will define a relation on the set of all the integers. Here in this notation, we do not write an n, we just suppress it. Of course, this relation will depend on n. So if you want to be very fussy, you can put a subscript here, but that starts cluttering things a bit too much. So we define a relation on integers as follows. For two integers x and y, we define or we write if and only if n divides the difference of x and y. So that's a relation, of course. That's a relation on the set of all the integers. And we want to say that it is actually an equivalence relation. Okay? So that's very easy. Why is it an equivalence relation? So we need to check three things. Reflexivity. What does reflexivity mean? It means that everything is related to itself. So is it true that x is related to itself under this relation? This is equivalent to saying that n divides x minus x, which is equivalent to saying that n divides 0, but that is true. So reflexivity holds. Symmetry. Symmetry is asking that suppose x congruent to y. I'm reading the symbol as congruent to. The symbol I'm reading as congruent to, but as of now I should just say x related to y. So suppose x is related to y under this relation. Is it true that y is related to x? So then by definition n divides x minus y. But if n divides x minus y, then of course n divides y minus x, which is same as saying that y is related to x. So symmetry also holds. And transitivity. So for transitivity, suppose x is related to y and y is related to z, small z. We want to show that x is related to z. But since x is related to y, we have n divides x minus y. And since y is related to z, we have n divides y minus z. Right? X related to y is same as saying that. Y related to z is same as saying that. Now, since n divides x minus y and y minus z, n will also divide the sum of these two numbers. So we get n divides the sum of these two. But minus y and plus y cancel out, so we are left with x minus z, which is same as x congruent to z. So transitivity also checks out. Very simple. So we have defined an equivalence relation on the set of all the integers. So for each natural number n, there is an equivalence relation on z, which we will refer to as the congruence relation. So this will be referred to as the congruence relation modulo n. Okay. And one more very important point, that instead of writing x congruent to y, instead of just leaving it at that, because this relation is sensitive to n, and in this notation we haven't captured the role of n, this will be written in this fashion. So to say that x and y are related under the congruence relation mod n, we notationally write it this way. And how do we read it? X congruent to y modulo n, or mod n. Or you can also read x equals y modulo n. X may be very, very different from y. X may be 1, y may be in 876. Still, you can say they are equal from the point of view of n. Right? And this kind of reduced way of looking at, a coarse-grained view of looking at integers is very useful. We'll see the power of this maybe in some examples, but for now, I'll just leave it at that. So let's proceed. So given any equivalence relation, we get equivalence classes. So suppose you have an equivalence relation on a set X, and let's denote the equivalence relation by tilde. Then the set X is partitioned by the equivalence classes under tilde. What are the equivalence classes? By definition, you pick any element in X. The equivalence class of X is all the things in capital X which are related to little x. That's the definition of the equivalence class of X. And we are trying to figure out what are all the equivalence classes. Two different equivalence classes do not intersect. So the equivalence classes partition the whole set on which the equivalence relation is defined, and all of this I'm assuming you already know. You know so much about equivalence relations, that much I'm assuming. So can we describe the equivalence relations? Can we describe the equivalence classes? Yes, we can. And let me first illustrate that via an example. Rather than giving the Cori description for an arbitrary general n, we will do that. But first look at the congruence relation modulo 4. So just a simple, concrete, small, friendly number. What is the equivalence class of 0? All the things which are related to 0. So the equivalence class of 0 is, by definition, we may denote it this way. And this by definition is, maybe I'll not use the color gray because that will confuse. So the equivalence class of 0 by definition is all those integers which are related to 0 modulo 4, which is all the integers which are divisible by 4. And those are these integers, the ones that have been plotted in pink. What is the equivalence class of 1? The equivalence class of 1 is those integers which are congruent to 1 modulo 4, which is same as saying 4 should divide x minus 1. And those are the things which are one shifted by the equivalence class of 0. So 1 and 5 and 9 and whatever this is, minus 3, I think. Yeah. So those things which leave a remainder of 1 when divided by 4, that is another way to say it. So that's the equivalence class of 1. And similarly, we have the equivalence class of 2 and the equivalence class of 3. What about the equivalence class of 4? Well, the equivalence class of 4 is same as the equivalence class of 0, because 4 is related to 0 under this relation. So there are exactly 4 equivalence classes. There are exactly 4 equivalence classes. Class of 0, class of 1, class of 2, and class of 3. all the possible remainders that you can leave when you divide something by 4, those are a set of representatives for all the equivalence classes, right? And I would encourage you to pause the video and try to describe the equivalence classes for any n. Try to do that. It's a very, very similar discussion. Okay, let's move on. So this notation will facilitate the expression of the set of all the equivalence classes. What notation? For any integer n, we will write nz to mean n times x, where x is an integer. So all multiples of n, which is same as saying all the things which are divisible by n. So that's the notation. It's a very nice notation. It's a very convenient and appropriate notation. This looks like a product of n with z. Of course, that's ridiculous. You don't multiply an integer with the set of integers. But the notation is so chosen so that the idea is conveyed very nicely. Okay, what about this? What is this notation? We have defined this notation, but what is this? So a and n are any integers. We define this thing as the translate of the previous thing by a. So a plus nx, where x is in z. So very handy notations, and they are natural. The notations are not contrived. Okay, so let's note that if we have some natural number n, and this is the congruence relation modulo n, then the equivalence classes under this relation are precisely nz, 1 plus nz, 2 plus nz, up until n minus 1 plus nz. Those are the equivalence classes. In case of n equals 4, we saw this in the previous page, but here I encourage you to fully be convinced of this. Do not be in a hurry to move ahead or anything. Try to digest all the notations and the statements. Okay, and the set of all the equivalence classes, is denoted by the funny notation, which requires a lot of comments, but for now, I'll just say that it is denoted by, we write a z, we put a /, and then we write nz. And we read it as z mod nz. Z mod nz. That's how we pronounce it. So, unclear why this notation has been chosen to represent this set, the set of all the equivalence classes under the congruence relation modulo n. But this will be explained in group theory. As of now, this notation is one single piece, but when we study group theory, which is a separate course, this is a group, that is a subgroup, and when you have a group and a subgroup, you can kind of divide the group by its subgroup, and that's what this notation is. But as far as we are concerned in this course, this is just one single fat piece to denote the set of all the equivalence classes, nothing more, nothing less. Okay, and let me also maybe draw a picture here just to suggest kind of at least some geometric or some visual way to keep in mind. We had the set of all the integers, which we imagine arranged in a line usually. And once you introduce the congruence relation mod n and plot out all the equivalence classes, you can kind of think that they are now arranged in a circle, right? So you have the congruence class of 0, then class of 1, 2, 3, up to n minus 1. And then what happens if you add 1 to n minus 1? It jumps into the equivalence class of 0. n minus 1 was in the penultimate equivalence class, but where is n minus 1 plus 1? n minus 1 plus 1 is n, which is same as 0 modulo n. So this number, it comes back to the equivalence class of 0. So 0 is here, 1 is here, 2 is here, and so on and so on. But then n is here, n plus 1 is here, n plus 2 is here, and so on and so on. So the thing goes around in a circle when you think of integers modulo n rather than their actual glorified nature. So this relation kind of folds this line into a circle, a discrete circle, but a circle. So that's one picture to keep in mind. Okay. And now what makes all of this stick? It is modular arithmetic, or the algebra of remainders, which is perhaps a better name. This is not, I don't think this name can be found in literature this way, but it is a very appropriate name for what is referred to as modular arithmetic. So fix some natural number and suppose A congruent to B modulo n and C congruent to D modulo n. So from the point of view of n, A and B are the same and C and D are the same, meaning this leave the same remainder modulo n, if you will. Then you can kind of play this algebra with them. Just like in equations, if these were like true equations, if A were equal to B and C is equal to D, you could have said A plus C is equal to B plus D. But you can do the same thing with even when you are taking a coarse-grained view. So A and C you can just add, put on one side, and B and D you can add and put on one side. Right? So that's very nice. And similarly for the product, nothing more complicated. So this behaves so nicely. Okay. So how do we prove this? Very, very easy. So since A is congruent to B modulo n, or maybe I'll be a little bit brief in my writing. So this implies n divides A minus B. The second one implies n divides C minus D. And now if we add, so just add these two, n will divide that also. If n divides this and that, n will also divide their sum. So therefore we get n divides A plus C minus B plus D. Too many brackets, which is same as saying A plus C is congruent to B plus D modulo n. Very simple. Okay, so what about this one? How do we prove this? So let's maybe, so let's do it in full detail. I don't want to leave anything as an exercise at this point. So this proves 1. Maybe I'll name them. So this is 1 and this is 2. And what we have done is we have proven 1. And now let's prove 2. Okay. So we have that again, A congruent to B mod n. This is given to us. This implies n divides A minus B, which implies, which I will write as follows. I'll just use the definition of division. A minus B is equal to, let's say, maybe, what's a good x? X is good, I think. Nx for some integer x. That's the definition of division. And similarly, since we are given that C congruent to D modulo n, we get n divides C minus D by definition, which means C minus D is equal to ny for some y in Z, some integer y. So the first equation is just reading that A is equal to B plus nx, and the second equation is C is equal to D plus ny, right? Which implies, so all I'm doing is that this gives that and this gives that. So now I'll just multiply these equations. These are honest to God equations in integers, and we can just multiply them. So the left side is AC, the right side is B plus nx times D plus ny, which is by a basic algebra, and times some garbage, but let me write down the garbage even though it's not important. The garbage is by plus dx plus nxy. So AC minus BD, this is a C, not very visible, AC minus BD is n times something, and therefore AC minus BD is divisible by n. So let me leave it at that. I am running out of space. So that's it. This proves that thing. I'm just skipping one small step. Just write AC minus BD as n times the garbage, and therefore we have what we wanted. So we have proven this very nice algebraic statement, and it has a corollary which is sufficiently useful to isolate. Again, suppose we have some natural number n and two integers a and b are congruent modulo n. Then you can scale both sides, just like in usual equations, by whatever integer you like. You are not going to be scaling with non-integers. Here everything, this whole game is about integers. Okay, so you can scale both sides with any integer you like, and still the congruence will be preserved. And you can also exponentiate by any natural number, not negative numbers. Doesn't make sense to write a to the power minus 2. Even though we will assign a meaning to it later, if it can be assigned, it cannot always be assigned. But for now, we are only going to be using natural numbers. So you can exponentiate by natural numbers, and this is just a corollary of these two. What about the first one? How does the first one follow from this guy? Well, let's say we were trying to prove it for k equals 2. We just use the fact that 2 is nothing, 2a is a plus a, and so what I'm saying is the following, being very silly. A is congruent to b mod n, we are given this. Just write it one more time. A congruent to b mod n. And apply the first one to this set of congruences, and we get 2a, because a plus a is 2a and b plus b is 2b mod n. Right, and now apply 1 to this set of congruences. A plus 2a is 3a, b plus 2b is 3b, and so on. So you can prove it for any scaling, and you can also prove it for negative integers, because if a congruent to b mod n, you can also see that minus a is congruent to minus b. So that I leave as an exercise, and then you can just upgrade it to any integer. But here in exponentiation, this I leave as an exercise, you just have to use it repeatedly. But here you can't say 1 upon a is congruent to 1 upon b, because that doesn't make any sense. You can't talk about divisibility in this non-integral setting. So you can't use negative indices, negative exponents here, but positive exponents, just a repeated application of the second one. So that's modular arithmetic. And now let's see the power of it. Such a simple thing which we developed in no time. We didn't develop it I'm not trying to claim any credit for it. This was developed by Gauss. But let's see the power of it. So we have this, we want to prove that 41, let me write a bigger 41. 41 divides this funny number. It's daunting if you just throw it at some high school kid. It may sound like a very bizarre thing to even ask. How can one possibly prove it? It will take 1 month to compute what this number is. So how can you possibly even check this part? With modular arithmetic, it's very easy. So we have 2 to the power, let's raise it to some power. So what about 32, 2 to the power 5 is 32, 2 to the power 6 is 64. So this is equal to 64, but I'll write it this way. Right? 2 to the power 6 is definitely congruent to 64, because 2 to the power 6 is equal to 64. But 64 is congruent to what modulo 41? So this implies 2 to the power 6 is congruent to 23 modulo 41. So what happened? All we are using is that 64 is congruent to 23 modulo 41. Right? Because their difference is 41. Is it? 4 minus 3 is 1. Yeah, it is. So 2 to the power 6 is congruent to 23. Let's raise it to power, let's square both sides. As we saw, we can square both sides. So this says that 2 to the power 12 is congruent to 23 square modulo 41. And we need to compute 23 square. So 23 square is God knows what. 529. So instead of 23 square, I'll write 529. But 529 can be replaced by a smaller number, because 529 will be congruent to whatever is the remainder of 529 when you divide it by 41. So let's divide 529 by 41. And this, I think, will go 2 times. So 2, 8, 7 and 3. So here we can write out 37. So 2 to the power 12 is congruent to 37 modulo 41. Right? And so this, let's isolate this thing. This is one thing that we have. Oh God. I am tired. Doesn't matter. So this is our star equation. And now another set of equations. So 2 to the power 4 is 16, which by squaring both sides gives us 2 to the power 8 is 16 square modulo 41. What is 16 square? 256. So here I can write a 256, but 256 can be reduced because we can just write the remainder of it modulo 41, which might 5 times or maybe 6 times. 6 times would be nice. 6 1 6, 6 24, 0, and this is a 1, so 10. This implies 2 to the power 8 is congruent to 10 mod 41. Right? So what did I do? I'm just saying that 256 is congruent to 10. 256 is congruent to 2 to the 8, but it is also congruent to 10. So 2 to the 8 is congruent to 10. So we are here, and this is our second equation. Another star here. So multiplying the 2 stars and erasing my rough work, multiplying the 2 stars, we get, and as we saw in the previous, we can multiply congruences. So 2 to the power 12 times 2 to the power 8 is congruent to 37 into 10 modulo 41. Right? What happened? We have the first star and the second star. We multiply the left hand side, we multiply the right hand side. We have just written it out. So this is 370. 370 modulo 41. But what is the remainder when 370 is divided by 41? So if I do 9 times, I get a remainder of 1. So this is congruent to 1 modulo 41. I'll erase the rough work. So what do we get? We get that 2 to the power 20 is congruent to 1 modulo 41. Why? Because this is 2 to the power 20. So we have this equation. Maybe I'll write a better 2 to the power 20. And this is same as saying, this is equivalent to saying that 41 divides 2 to the 20 minus 1. So there is no need to calculate 2 to the power 20. Every time you exponentiate and your, this thing runs above 41, you reduce it by taking the remainder. So this is not the most efficient way to do it. There is a much more efficient way to do it. But I just wanted to, I illustrate that even with bare hands, you can compute these things. You can write a very efficient computer code also. Anyway, so that's one example to illustrate. The other thing, another daunting looking division problem. This horrible sum, we want to show when you divide by 9, when you divide by 12, leaves a remainder of 9. Right? So again, there is no need to compute 100 factorial. Nobody can do that. But we can immediately, this we can solve very quickly. So note that 4 factorial. So 4 factorial is divisible by 12, which I will write this way. And in fact, this implies that n factorial is divisible by 12 if n is at least 4. Because 5 factorial already has 4 factorial contained in it in this sense. So if 12 divides this guy, 12 will of course divide that guy, and so on and so on. So for n greater than equal to 4, this holds. So in that sense, you can, when you're taking this modulo 12, you can forget about everything that comes after. So you can write that this summation k factorial, k running from 1 to 100, this thing is equal to or congruent to 1 factorial plus 2 factorial plus 3 factorial modulo 12. Because everything after 4 factorial and onwards gives you 0 modulo 12. So you can just write this number, but what is this number? This number is 6 plus 2 plus 1, which is 9. So that's it. Therefore, and 9 is less than 12, so therefore 9 is the remainder that this number will leave when you divide it by 12. Very, very short solution. And one more, we'll see many more. This kind of question is very popular in high school mathematics also. Usually these are tackled using binomial theorem, but the correct way to do it is modular arithmetic. And even with the rudimentary version of modular arithmetic, there are many theorems in modular arithmetic that speed up these solutions. But for now, we have the bare bones version of it. Even that is very powerful. So we want to find the last digit of this horrible thing. How do we do it? Asking for the last digit is equivalent to asking the remainder when you divide something by 10. The last digit is nothing but the remainder left when you divide that number by 10. So we are asking for the remainder of this when it is divided by 10. But, so let's find the remainder of this and that separately, and then we'll proceed. So 3 to the power 2 is what we want to talk about. But first, 3 square is, I'll write the statement and let you verify. Right, because 9 minus 1 is 10. So this congruence holds. And therefore, we exponentiate both sides to 111. And the left side is 3 to the power 222, which is congruent to minus 1. Mod 10. Why minus 1? Because this number is minus 1. So we have this we write as star, put a star here. And we'll play the same game with the other guy. So 2 to the power, so what's a good thing here? So 2 to the power 3, 4, 5 will be 32. Okay, let's run with it. I mean, let's try 5. So 2 to the power 5 is 32, mod 10. But 32 is congruent to 2 mod 10. Right? 2 to the power 5 is congruent to 2 mod 10. So therefore, 2 to the power 5 to the power 5 is congruent to 2 to the power 5 mod 10. We just exponentiated both sides by 5. But as we saw, 2 to the power 5 is congruent to 2 mod 10. And here we have a 2 to the power 5, so I can just write a 2. I can just write a 2. So 2 to the power 25 is congruent to 2. This much we know. Okay. I'll square both sides. So if I square both sides, I get 2 to the power 50. Or maybe let me raise both sides to the power 4. So 2 to the power 100 will be congruent to 2 to the power 4 modulo 10. Right? All I did was raise both sides to the power 4. 2 to the power 4 is 16. 16 is same as 6 modulo 10. I'm being a little bit fast, but I hope you follow. This is 6. And now I'll raise both sides to the power 3. So I get 2 to the power 300 is congruent to 6 to the power 3 mod 10. But 6 cube is 216. 216 is same as 6 modulo 10. 216 is same as 6 modulo 10. Great. Now I'll multiply both sides by 2 to the power 25 again. But 2 to the power 25 is congruent to 2, so I can write a 2 here. 6 times 2 is 12. 12 is same as 2 modulo 10. So we are nearing it. We have reached 2 to the power 325. We are short by 8. So both sides we will multiply by 2 to the power 8. So 2 to the power 325 times 2 to the power 8 is congruent to 2 times 2 to the power 8 modulo 10. 2 to the power 8 is same as, what is 2 to the power 8? I think it's 256. 256 is same as 6 modulo 10. 6 times 2 is 12, which is same as 2 modulo 10. So 2 to the power 333 is congruent to 2 modulo 10. So this is our another star. Now, using this star and that star, if we add both the signs, what do we get? If we add both the sides, we get 3 to the power 222 plus 2 to the power 333 is congruent to minus 1 plus 2 mod 10. Minus 1 plus 2 is 1. So the remainder of this guy, when you divide it by 10, is 1, and therefore the last digit of this number is 1. Okay, let's proceed. Okay, so now we will revisit the old examples that we proved by just using the remainder with division theorem. But this time we will use modular arithmetic. So this we saw earlier. How do we prove this? Well, very quickly we can do this. 2 cube is congruent to 1 mod 7. Right? Because 2 cube is 8. 8 minus 1 is 7. So this is true. Raise both sides to the power n. 1 to the power n is 1, so I'll not worry about writing it. And this is same as saying 7 divides. No stupid binomial expansion or anything. One line solution. You can do it mentally, in fact. Don't even need to write anything. We also saw this one. So let's see how we will manage this using modular arithmetic. Well, there are a bunch of possibilities. N is either congruent to 0 or 1 or 2 or 3 or 4 or 5 modulo 6. So what are we trying to do? We will just show that this thing is congruent to 0 mod 6. So this is what we will do. Right? Showing this is an integer is same as saying this is divisible by 6, which is same as showing this. So that's what we want to do. Now there are 6 cases. There are these 6 cases in the, and I will list out the possible things in this order. So if n is congruent to 0, n plus 1 is congruent to 1 or 2 or 3 in this order. Let me explain what I did. There are 6 cases. N is congruent to 0, in which case n plus 1 will be congruent to 1. Or if n is congruent to 1, n plus 1 will be congruent to 2. And so on and so on. If n is congruent to 5, n plus 1 will be congruent to 6, but 6 is congruent to 0. So n plus 1 is that. And now 2n plus 1 will be congruent to 1 or 3 or 5 or 7. But let me write a 7, 9 and 11. So what am I doing? 2 times 0 plus 1, 2 times 1 plus 1, 2 times 2 plus 1, and so on and so on. But in place of 7, I can write a 1. We are only worried modulo 6. In place of 9, I can write a 4. Not 4, sorry. I can write a 3. And in place of 11, I can write 5. Yeah, so this is there. And therefore, n into n plus 1 into 2n plus 1 is congruent to one of the 6 things. 0 times, so in the first case, we get 0 times 1, which is 0. So that's clearly 0. In the second, we get 1 times 2 times 3, which is 6, which is also 0, because modulo 6, 6 is 0. 2 times 3 times 5, which is 6, into 5, 30. 30 is divisible by 6, so I'll write a 0. And you will see that all of them will be 0. All the 6 will be 0. So modulo 6, all these 6 cases, when you product out, always get 0, and that's it. 6 divides this guy. Again, later we'll prove a little bit more about integers where so much computation will not be needed. But for now, this is good. This also we saw, if you have any integer, then its square can leave a remainder of either 0 or 1 modulo 3. How do we do it? Again, we have 3 cases. You take any integer, either it is congruent to 0 or 1 or 2 modulo 3. Only 3 cases are there, which means x square is congruent to 0 square or 1 square or 2 square modulo 3. But 0 square is 0, 1 square is 1, and 2 square is 4, but 4 is 1 modulo 3. And that's it. So if you square any integer, you will only see 0 or 1 modulo 3, which is exactly the statement. So that's nice. And yeah, so if 3 divides x square, then we want to show that 3 divides x. So let me leave this as an exercise. I mean, not much of modular arithmetic is here, but all you do is you just consider this case, x square congruent to 1, which is same as x congruent to 1 or 2. Anyway, let me not speak about it. And now lastly, we want to show that if this is divisible by 3, then individually x and y are divisible by 3. So if 3 divides x square plus y square, what do we have? We have x square plus y square is congruent to 0 mod 3. This is given. But now either x square is congruent to 1, in which case this can never hold. Why? Because if x square is congruent to 1, there are 2 cases. Either y is congruent to 0 or y congruent to 1. But if x is congruent to 1, then either you add 1 and 0 or you add 1 and 1. You are not incurring 0. You're incurring 1 and 2 as the remainders. I hope we followed. If x square is congruent to 1 modulo 3, and y square then doesn't matter regardless, either it is congruent to 1 or 0, x square plus y square will be either congruent to 2 or 1 modulo 3, which means x square plus y square is not congruent to 0 modulo 3. So x square cannot be congruent to 1 modulo 3 if this were to be true. Similarly, y square cannot be congruent to 1 modulo 3 if this were to be true. The only other case is x square is congruent to 0 modulo 3 and y square is congruent to 0 modulo 3. I'm using this exercise all the way. So this implies x square is congruent to 0 modulo 3 and y square is congruent to 0 modulo 3. But now using the previous one, this shows that 3 divides x and 3 divides y. Right? I think this is it. Let's see. Yeah. So I hope this is a good introduction to modular arithmetic. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.